Today's video is possibly the most important one to do with capacitors. Capacitors is a field, an area, where there is always a question in the exam. Now I say that, and of course there won't be the next time, but in paper 1 for the A-level, you're pretty much guaranteed to get a question, some form of question about capacitors. It may be combined with other parts of electricity, so you need to watch out for that, but let's talk about charging and discharging a capacitor. So this is the circuit that you use, and if you are looking for the core practical that goes with this, I've already done a video on the core practical. I will link to it at the end of the video so you can see it. It shows you the data that you get for discharging a capacitor and also what happens when you put square wave AC through. So this is the circuit that you use. In this circuit you can see we have a two-way switch right here. And the two-way switch is there so that when you move it to the left, your capacitor is connected in with the battery, and so the capacitor charges. And then when you move the switch to the right, the battery is no longer part of the circuit, and the capacitor becomes the energy source for the circuit, and then the capacitor discharges through this resistor R here. A lot of people get hung up on the mathematics of capacitor charge and discharge, and it is important to be able to use the equations which we will come to later. But you also have to really be able to explain what is happening physically here. So let's think about charging. When you close this switch onto the charging circuit, then imagine the electrons that are running through this circuit, and they begin to pile up on this plate of the capacitor. Now obviously your conventional current is running in the opposite direction, but the electrons begin to pile up. They create an electric field across the capacitor here and repel electrons on the other side, and so you get effectively a complete circuit with your two sides of the capacitor being opposite charges. So electrons pile onto the negative plate, that repels electrons from the other plate, and a potential difference is created across the capacitor. So the potential difference across the capacitor increases. And it increases exponentially, which we will get to in a moment, but it will increase until the voltage across the capacitor is equal to that across the supply. And that is the maximum voltage that you can get across the capacitor. And so you'll see the value on the voltmeter increasing until it matches the value of the voltage of the supply. We will come back to this circuit later to talk about discharging the capacitor, but for now we want to look at what happens to the charge and the voltage across the capacitor as you charge it, and also what happens to the current in this charging circuit. Let's talk about the charge on the capacitor first, because this is the fundamental part. This is what causes everything else. And if you think carefully about adding charge onto the plate of the capacitor, the first coulomb of charge goes on very easily because the capacitor is empty. The next coulomb of charge is a little bit more difficult to put on because there's already a coulomb of charge there that's going to repel it. The third coulomb of charge, a little more difficult again. So if you think about the buildup of charge, it's going to start pretty quickly. So they go on easy at first, but as time goes on, you get an increasingly repulsive effect from the charge that's already on there, and so the rate at which the charge gets added on becomes less and less and less. And hopefully that makes sense to you, until you get to the point where the potential energy of the charge that's already on the capacitor is equal to the potential of the battery. In other words, the voltages are the same. So as you add charge on there, remember it's like winding up a spring or pushing two magnets together. As you add charge on there, the potential energy of each coulomb of charge increases. And of course, that potential energy is voltage. So if we look at what happens to the voltage across the capacitor with time, we should expect to see a somewhat similar graph. And in fact, we do. Don't look at the numbers on the y-axis here. These are percentages of total. But if you look at the shape of the graph is exactly the same as the charge, because the addition of charge is what's causing the voltage to increase. And so again, our voltage starts to increase rapidly at the start, but over time, because it becomes more difficult to add charge on, our voltage again increases at a slower rate as time goes on. And this is an exponential increase. Again, we'll come back to that later on. What about the current in that charging circuit? Well, let's think about the motion of charge, because we know that current is the rate of flow of charge. So if we go back to our charge graph, here we can see that charge goes on pretty quickly at the start. So we would expect to have a high current at the start. But again, as it becomes more difficult to add charge, we're getting less and less charge put on with time, and therefore we would expect our current to drop with time. And of course, that's exactly what happens. So we get our maximum current at the very start of our charging process, and very similarly, we get this decrease of current. The same sort of idea, but in the opposite direction, if you like. This one is a decrease, an exponential decrease, rather than an exponential increase. And interestingly, if you rotate this current against time graph around the x-axis, you will see, and I've literally just done that, you will see that of course you get a graph that is very similar in shape to the charge against time and the voltage against time graph that we had, showing that we are looking at the same relationship, just rotated about that time axis. So instead of increasing in that way, this one is decreasing. In our original circuit, we didn't have any resistor in our charging circuit, and you can put a resistor in there. And what that resistor will do is that it will slow down the charging process. So if you don't have it there, your capacitor charges almost immediately. If you do have it there, the capacitor will charge more slowly over time. What this does is it adds an extra element into our capacitor charging and our capacitor resistor circuit. So let's have a look at what the graphs would look like. The voltage across the capacitor and charge across the capacitor, and then what it would look like for the resistor. Now here on the left-hand side, we have our two graphs for the charge across the capacitor and the voltage across the capacitor, and also the current in the circuit up there. So these are the three graphs we've seen before, but interestingly, and something that comes up quite a lot in exam questions, is what would the voltage across the resistor look like? So if we compare the two graphs at the bottom here, you can see that the voltage across the capacitor is increasing as expected, just like we saw before. But of course, the resistor is in series with the capacitor, and we know that in a series circuit, the voltage is shared amongst the components in that circuit, and there's no exception here. So for the resistor, we would start with the maximum voltage across the resistor, because when the capacitor has zero voltage, the resistor will have the same voltage as the supply. But then over time, the voltage across the resistor is going to decrease as the voltage across the capacitor increases. And so if you added up at any particular time, if you added up the voltage across the resistor and the capacitor, it would equal the voltage of the supply. Charging circuits have become more popular with examiners recently, but of course, discharging is the main topic here. And so to discharge the capacitor, you move your two-way switch over to the right-hand side, and the capacitor becomes the supply for the circuit. Remembering, this is the negative side of the capacitor, and this is the positive. And what's going to happen, of course, is as soon as you move that switch, charge is going to flow off the negative end of the capacitor, round through the resistor, and back to the positive end. But again, our conventional current, remember, goes from positive to negative, so if we were asked to label which direction that current is going, it's always from positive to negative. And of course, what's going to happen is, as charge flows off, we can readily see that the charge on the capacitor is going to decrease over time. And again, remember, the rate at which charge flows off here, how quickly that charge flows off, is going to decrease over time, because that charge is flowing off because each coulomb of charge is repelling every other coulomb of charge. And as charge flows off, that repulsive effect becomes less. And so at first our charge is going to flow very quickly, and then over time it's going to become less and less and less. And we can probably start predicting what those graphs are going to look like. What about the voltage across the capacitor? Well, of course, the voltage is the potential energy of that charge. So at first, it has its maximum potential energy. the voltage will be equal to what we charged it up to at the start, which is that of the supply, the original charging supply. As the coulombs flow off the capacitor, we know that the potential energy of the coulombs that are left is going to decrease. And it will decrease in the same way as the charge decrease. So again, we can possibly start to predict what those graphs might look like. The current through this circuit, if you were to put an ammeter in the circuit here, again, current is the rate of flow of charge. So we know that at first, because the charge is going to come off quickly at first, we're going to have a high current, and then as the charge starts to slow down, our current is going to decrease. And as predicted, that's exactly what happens. We start off with our maximum charge here, and over time, that charge flows off the capacitor, but the charge on the capacitor and the loss of charge on the capacitor decreases over time. Same idea with the current. We've said this before. The current is the rate of flow of charge, and so we're going to start off with a very high current as that charge gets pushed off the capacitor, and then our current decreases over time in the very same way. And as we've said, the voltage occurs the same way. Now I'm using this particular VT graph, which I took from the work that I did for Core Practical 11, because this is actual data. This is for a 100 microfarad, 484 kilo ohm circuit. And I mentioned these numbers because these numbers are very important. And let's think about why. And let's look first of all at the resistance in the circuit. Now we know that the resistance in the circuit is going to determine the current. And the current is the rate at which charge flows off the capacitor. So the resistance in the circuit is going to determine the slope of this graph over time. If you have more resistance, the capacitor is going to discharge more slowly. What about capacitance? We know the capacitance of a capacitor is how much charge it will hold per volt. So a higher capacitance capacitor holds more charge per volt. And capacitance then has the same effect as resistance. The higher the capacitance, the more slowly it will discharge over time because it's able to hold more charge. And these numbers are very important. When you encounter capacitor questions in which you are given these numbers, the first thing you should always do is calculate the value of what's called the RC. If you multiply these numbers together, we get an RC of 48.4. And that has the unit of seconds. If you look through the unit of capacitance and the unit of resistance, and you take it down to its base units, you'll find it works out as seconds. And that's a very important idea. This notion of the RC, the combination or the product of the resistance and capacitance of a circuit, is given the Greek symbol tau. And this is the time constant of the discharge or indeed charge circuit. And usually we just call it the RC. But it does have an official name, the time constant. What that is the time it takes for the, in this situation, voltage to fall to 1 over E of its original value. And if you don't know what E is, it's a constant number called Euler's number, and it is associated with exponential curves. You can delve deeper into Euler's number if you like, but for us, we just need to know exponential curves have E associated with them. What this RC value tells me is that for this circuit, it should take 48.4 seconds to fall to 1 over E of its original value. And 1 over E is 36.7%, or 0.367. So if you multiply your original value by 0.367, then you should get what your RC is. Sometimes you see that just rounded to 37%. You can use either one simply because there's usually a bit of uncertainty in capacitor circuits anyway. Importantly, 5 RC, so 5 times our time constant, is usually considered for full discharge for a capacitor. So when you have completed 5 RC, the capacitor has fully discharged. Of course, as an exponential curve, it never actually discharges to 0. We get to the point where there's a negligible amount of charge left on your capacitor after 5 RC. We can use a graph like this to find the RC. of a circuit if we don't know it. And to do that, we simply say, okay, our original voltage, and in this case it was 5.95 volts, multiply that by 0.367, which gives us 2.19 volts. And if we find 2.19 volts on our graph, and we go across, and we go down, we should be able to get a value for the RC of the circuit. And we know it should be 48.4 seconds. And in fact, that looks very close. If you have a graph like this, you don't just do it once. You would find 36.7 of that value, 2.19, do it again, and take an average, and if you can, even a third time. So if you have to find the RC from a curve like this, make sure you do it repeatedly so that you can take an average. And the sort of question would ask you, okay, find the RC if the capacitance of the capacitor is blah, what is the resistance in the circuit? And so you would then use the RC value to find that. So this concept of RC is super important for all capacitor circuits. Make sure that you know how to get it from an exponential curve like this, and we will look at some other ways of getting it, or what it means, because it determines the rate of decrease of your charge, your voltage, and your current in a circuit like this. And just to illustrate that, look what happens if you change up the RC. Well, these are oscilloscope traces, and every one of these started with 6 volts, and the time period is 0.02 seconds. And for this particular discharge, 2.2 kilo ohms and 100 microfarads. And if we go ahead and calculate the RC of this, the RC of this is 0.22 seconds, which means it would take 0.22 seconds to fall to 37% rounded of the original value. Now, considering that our time here is only 0.02, we can see that we would need 10 times the x-axis here in order to see the graph fall to 37%. And so it looks like a sloping straight line because we're only seeing the very start of this. Because of the size of the capacitance and resistance, in 0.02 seconds we don't get much of a fall. And so don't be fooled if it looks like a horizontal straight line and you're told that it's a capacitor discharge. It could be that the RC value is so high that in the time of the graph that you're looking at, you don't see significant loss of charge or volts or current. Now, if we decrease the RC, here, if you do the calculation of RC, you get a value of 0.0134 seconds. And so we can see in 0.02 seconds, we have already fallen to 37%. And so our graph looks more like a slope, and we can even see the curve coming in here. And 5 RC for this would be 0.0675 seconds. So if we had 3 or 4 times the x-axis here, then we would see that the capacitor has discharged fully. It's gone through 5 times its RC, and it's effectively lost all of its charge. So the time here on the x-axis is very important to be able to interpret these graphs. Finally, in this situation, so we've got 1000 ohms and 4.7 microfarads. We have decreased the capacitance quite a lot here. And you can see that we are pretty much going through the full discharge. But let's look at the RC to be sure. So our RC here is 0.0047 seconds. And 5 times that would be 0.0235. So we're almost, after 0.02 seconds, we're almost fully discharged. We need just this little last part, 0.0035 of a second, to get to full discharge, but effectively we're there. So again, look at your RC, match that to the time the circuit is discharging for, and you'll be able to see how much of the capacitor will have discharged in that time. Now let's look at the actual equations that go with them, and you need to be able to use these equations. And let's pick them apart a little bit. We already said that the RC value is the value that determines how fast the capacitor is going to discharge. And if you've got a greater RC value, you've got a slower discharge. And that's what this equation is telling us. Because this V is, we're taking the voltage graph to start with, this V is the value of the voltage after this time. Now, if you've got a very large RC, and you're looking at a very small time interval, then you would expect that your V would not be all that different from your V0. It hasn't decreased very much. And so our voltage is proportional to the voltage that we had at the start. That's one of the definitions of an exponential relationship. And then, of course, it depends on the RC. What we also know is that V is equal to I times R. And so we could put I times R in here to get this version of the equation. I times R is equal to IO, our original current, times R multiplied by E to the power of minus T over RC. And of course, our R's here, because the resistance in the circuit is constant, are going to cancel. And we're going to be left with this equation. The current after a particular time is proportional to the original current that you had and is affected by the RC. And of course, we knew that when we talked through what was happening at discharge, we know that the voltage, the current, and the charge all behave in the same way when the capacitor is discharging. We also know that I is equal to Q over T. That is, current is the rate of flow of charge. And so we can substitute Q over T for our I and IO here, giving us this equation. These T's are going to be exactly the same. And so we're going to cancel those T's out and be left with Q equals QO e to the power of minus T over RC, which of course we were expecting because, again, originally we said the charge, the current, and the voltage are all going to decrease in the same way as the capacitor discharges. We know we're going to get a nice curved graph if we plot Q against T. The trouble with curved graphs is that a best fit line is not as accurate on a curve as it is on a straight line. In order to make our results more accurate, so that we can read off the graph more accurately, we need to try and turn this into a straight line. And to do that, we're going to take the natural logs of both sides. The natural logs rather than log to base 10, because with natural logs, E, the natural log of E, is 1. And when we do that, we get this. ln Q equals ln Q0 minus T over RC. And of course, we could do the same thing for our current, giving us ln I equals ln I0 minus T over RC. And for our voltage. And this is the one we're going to work on. I'm going to rearrange this equation slightly so that it looks more of a format that we can recognize. And I'm rearranging it to this. And the reason that I'm doing that is because, as usual, we like nice, straightforward, straight line equations. And so that is in the format of y is equal to mx plus c. And so if you plot ln v on your y-axis and t on your x-axis, your gradient of your line will be minus 1 over RC, and so we would expect to get a negative gradient, and then the value of that will be 1 over RC, and our intercept will give us the natural log of our original voltage. And so we can use these values from a straight line graph to find whatever of these we need to. And here is the plotted graph of the original discharge voltage data that we had just logged. So you'll see we have ln v against t. Please note the way that you need to write log or natural log axes labels. They expect the brackets in these positions. And here, of course, we can see what the gradient is. So from that, we'll be able to get our value of RC, because minus 0.0203 is equal to minus 1 over RC. That means that our RC value here is 49.3 seconds. We can then compare that to our known value of RC, which was 48.4 seconds, and find a percentage error in our experiment this way. Capacitors do have what's called a tolerance usually 20%. Sometimes it can be 5% if it's a very good capacitor, but 20% is the leeway that you get in the RC value. So that's going to be within 20%. Our LNV0 here is 1.762, as you can see. And if we do e to the power of 1.762, which is the anti-natural log, we get 5.82 volts versus our known value of 5.95. So again, that could be used to find the percentage error. And let's think about the questions that you'll get with this. You could get this graph in paper 3 of the home A-level. You might have to plot it and then use it to find the RC and then use that for figuring out how long the capacitor is going to take to fully discharge. There is one thing about charging and discharging the capacitor that I haven't actually mentioned, and that's what's this RC value for charging. So let's go back to our charging graphs and see. We know with our discharging graphs that the RC is the time it takes for the original current, voltage, charge to fall to 1 over E of the original value, or 37% of the original value. We also know that these charging curves are symmetrical about the x-axis with our discharging curve. So let's go back and look at that again. Our current through a charging circuit for a capacitor follows the same shape as our discharge curve. And so we know that our RC for our charging circuit would be the time it takes to fall to 37% of the original value. Now let's flip this like we did before and see what the RC means for graphs that are in the opposite direction. If we look at the same time value, it's not, of course, 37%. Now it's flipped, and this is the time it takes for the capacitor to charge to 63% of its full charge, or if you're looking at voltage, 63% of the full voltage it's going to get, which again is the same as the voltage of the supply. So for charging curves, those positive curves, it's 63% represents our RC, and for discharging, it's 37%.